So thanks, everyone. As he said, I'm Rich Harang. I am a director in Sophos's data science group. And yeah, today I'm basically going to present you with a long list of lessons learned from the School of Hard Knocks. So my background, in addition to my academic background, I've been at the intersection of machine learning, network, and endpoint security for about 8 years now. At the moment, I'm leading most of the new research within the Sophos data science team. These are projects that run on multiple scales from just one person all the way up to 4 or 5 people on a single project. Most importantly, for the purposes of this talk, I think I've stepped on just about every rake there is in terms of running a project. And so now I'm going to tell you about them so you don't have to do the same. So this is the Sophos data science team. That's me in the top row. If any of the stuff that we're talking about here sounds like it's up your alley, come talk to me. I am wearing a blue I'm hiring wristband. We can stick you down in the lower right-hand corner. Exact position to be decided over beers. So this talk is going to be about sort of the process around doing a security data science project. So what, why, and how. What I am not going to talk about is a specific security data science project that we attacked, or a specific model, framework, or what the best ML framework is and why it's PyTorch. So I gather I'm supposed to give you sort of a key takeaway that I want you to remember, and that has to be in the first 3 minutes, so here it is. What most people sort of think of as their job as a data scientist is spending a whole lot of time doing fun programming and fitting models and tinkering with stuff. And yeah, maybe there's a little bit of talking to the consumers of the model, or doing a little bit of data wrangling, or writing stuff up for publication and stuff like that. In reality, this is what you should be doing. Most of your time should be talking to people, talking to external customers, talking to people within your group, talking to other people working in the same field. Unfortunately, most of the rest of your time is going to be spent wrangling data and cleaning it, and then you do actually get to do a little bit of the fun stuff, fitting models, programming them, using the latest, greatest academic research. Over my 8 years in this industry, this is the single best predictor of success for a security data science project that I've found. Know who's going to use it, talk to those people, have a continuous sort of cycle of collaboration, feedback, and updating going on within your team and to the end users of your project. So let's sort of start off with the why of all of this. So we've got sort of you see different versions of this, and this is a little ML-centric, but it applies to sort of more general data science analysis projects as well. We have this notion that we have some data, we train a model, we do an analysis, we make a decision, we do some sort of validation on that, check it against reality, we deploy it, we deliver it, we hand off the report, someone implements the decision, and we go around and we collect more data, and and on and on and on. And so this is all you need to know, right? Start with the very first question: what are we actually trying to accomplish here, right? So how is this model going to be used? What kind of decision is this analysis going to drive? Can we just answer one question and then stop, right? Is this a problem that I could solve with a regex, right? I know it is our God-given right as data scientists to run up $50,000 in cloud costs to figure that out, but let's see if we can simplify the process. So know what good enough is, and then really be able to say in concrete terms, right, what are we trying to do with this project? So with that in mind, we sort of go back to the cycle, and now we've got some questions that we want to be thinking about as we move through these steps, right? What features, what level of accuracy do we want to train it to? What metrics do we want to use? What ones have we agreed on with maybe our customers or internally? Where are we going to deploy it to? Who's going to receive this report? How do we have to phrase this analysis in a way that they can understand it and implement it? And where are we going to get the data from? How are we going to label it? How are we going to curate it and make sure it reflects what we need? So if you're coming to this from a data science point of view, very often when you're talking to external customers, they don't necessarily know what they want, or they may just want some of that hot new ML pixie dust that they can sprinkle on all of their efforts. So in some cases, you kind of have to be an educator, right? What are the trade-offs you can offer? What's realistic, right? So yes, they want something that can detect, zero-day exploits in encrypted network traffic. Maybe sort of bring them back a little bit and tell them what you might actually be able to deliver. probably the most important thing is get something concrete out of them, right? In order for this model or this project to be cost effective, I need to be able to get, this detection rate with this false positive rate, or I need to be able to realize this much revenue from these customers, or whatever it is. But map it to something concrete and measurable and negotiate that up front. So before we get into the how part of this presentation, which is going to be the bulk of it, you really should have sort of 3 questions nailed down. So you need to have talked with your external partners enough to know how your project is going to fit into the business somehow, right? A project that nobody needs and nobody can implement isn't something that's adding value for your organization. The person who's receiving it should have a good idea of what exactly it is you're giving them and how to interpret or use it, right? What are the inputs that are going into it? What are the inputs that went into it? What's going to come out of this model, or what's the decision that you're recommending in the report, and how should they interpret it or use it? And then everyone needs to be on the same page as far as how do we know when we're done? What does this mean to be successful, and how exactly are we going to measure it? Okay, so the how part of this. So these are kind of like 6 key things that I came up with as I was trying to frame up this process. They're kind of chronologically ordered. I know there's a lot of overlap between them. You can probably debate like which, maybe good features should go under be scientific or something, but just at a high level, these are kind of this is kind of how I thought it sort of split out. So data, let's talk about data, right? This is data science after all. So I have exactly 3 quotes in this slide deck. I have front-loaded all of them so you don't have to sit through them. Basically, John Tukey said that just because you've got data and you've got a question doesn't mean that you get an answer. Ronald Coase is the source of the follow-up to that if you torture the data long enough, you will indeed get an answer. And then finally, Norbert Weiner had the comment that the best model of a cat is the cat, right? So if you are dealing with some sort of real-world data, which presumably you want to ingest at some point, the data you use in your project, be it your analysis or training your model or writing up your report, needs to be as close as possible to the real-world data that you're actually using. You need to get your hands on that up front as soon as you can. So things to consider in this, especially if you're doing an ML project, are things like label distribution, label bias, data collection bias. If you're collecting, if you're doing a malware detection project and you're collecting malware from the internet, that may not look like malware that's going to arrive on your customers' endpoints. So you need to think about how you're going to sort of align those 2 data sets in a way that you're going to get a model that answers the questions that you actually want to ask. So this is something I'm going to keep coming back to in these slides, the security difference. So what extra things you have to think about when you're doing a security data science project versus sort of a plain old data science project. And in security, right, the bad guy gets a vote. So they're trying to obscure labels. They are adapting constantly, right? There's a cat and mouse game going on all the time. And in a lot of cases, it might not even be worth using old data, right? I have a very lovely, carefully curated collection of DOS viruses, right? I'm not sure I want to train my malware model on those anymore, right? I'm not sure that they're relevant. So when it comes to data, what should you actually be doing? The gold standard is going to be getting telemetry from deployment. If I can get real-world data, that's my gold standard. If you can't get that, if you've got to like mock up a proof of concept before they'll let you at the precious bits, then there's some other things you can try, right? Are other people working on similar problems? Especially in academia, this is sort of a criminally underutilized resource in this industry. Very often, if you talk to an academic researcher working on the same problem and say, hey, I'm working on this too, want to collaborate, want me to cite your paper, they will fire you the data almost as fast as you ask for it. So if you've got like an academic paper that's tackled the same problem, ask. They'll very often be willing to share. Sometimes you can buy the data outright, for malware or maybe malicious HTML or malicious URL problems. There are a lot of commercial feeds that you can license and just start pulling in data from those. sometimes there are existing data sets that, bearing in mind questions about label and sample bias, you may be able to pull in and use those at least to bootstrap a little bit. So again, in the malware space, Kaggle had Microsoft's malware data set, which has the header stripped from it, so it's not perfect, but at least it's a starting point. If you're doing like something with web-based detection, you might look at like the Common Crawl data set, which basically has tried to spider large chunks of has tried to spider large chunks of the internet. So look for other sources that you could maybe sort of adapt to your own nefarious ends. Especially in the security space, labels are something to be very, very critical and careful about. A very common thing is doing vendor aggregation. So if you have like a threat intelligence feed where multiple vendors are giving scores for multiple artifacts, doing a vote over those is a pretty common choice. But again, academic literature is your friend here. If you look up that process, you can find a lot of papers that talk about different ways you might want to think about doing that voting. Crowdsourcing is another option. It can be expensive. It can be difficult to implement, but once you sort of knock the bugs out of it, it can be a very good way to collect labels for less sort of technically oriented artifacts. You might not want to try it for like malware samples, but for things like, is this a phishing web page or not, you can usually get pretty good results. Finally, you can go back to the machine learning literature and you can do things like self-supervised labeling from a seed corpus. This can be buggy, this can be a little bit tricky, but it often gives you sort of a good head start on labeling data if you can form a nice small set of very cleanly labeled data. When you're doing train and test splits or train and validation splits, because this is a cat and mouse game, because adversarial samples change over time, and what was a hot malware threat 6 months ago might not be one in another 6 months. Very often your train test splits need to mimic deployment, which means splitting it temporally. So train on the earliest stuff, validate on the middle chunk, test on the newest data. If you don't do this, if you mix everything up and you just do random k-fold, 5-fold validation, you're going to get wildly optimistic results, because when you deploy it in the field, you've basically trained the model to expect data from the future. Finally, this is something I don't think I see quite enough talk about. Think about what data you actually want to keep, right? GDPR is a real concern. You should be worried about it. The risk of what happens in a data breach is a real concern. You should be worried about it. So, everyone talks about, I've seen very, different variations on this metaphor, as security data is oil, security data is toxic waste. My own contribution to the ongoing, data is X. Just think of it like plutonium, right? It can be really powerful. You can do a lot with it. It's got a shelf life, and you want to make sure that you store it and handle it really carefully. Talk with legal early and often. I am not a lawyer. I don't even play one on TV. But when you're talking about storing data, especially stuff that has potentially personally identifiable information on it, talk to your legal team early, often, and repeatedly. A lot of times you can transform data, so you can do stuff like tokenization or hash the features or store extracted features that might not have the PII. But remember, the only data that cannot ever possibly be breached is the data that you're not keeping. So think carefully about what you actually need to store. And again, talk with legal early, often, and frequently. Finally, and so this is one rake that was particularly painful to step on. When you have a good data set, protect it. It needs to be read-only, right? The danger here is not that you're accidentally going to delete it. No, that's like the best case, worst case scenario. What you really don't want to have happen is accidentally modify the data in place, not realize it for 3 months until you've been training on it for the past 3 months and realize that all of your results are crap because you've screwed up the data. So when you've got a good data set, you've got nice labels for it, it's pristine, it's beautiful, store it under a different account, and make sure that every other account that has access to it only has read-only access. If you need to modify the data set somehow, you should make a copy of it, right? Local copy, work with it separately. So the next thing I wanted to talk about a little bit was internal collaboration. Have one way of doing everything important, right? Never reinvent the wheel, and make sure everyone on the team is using the same tools, frameworks, and so forth. You can get a lot from open source code, especially if you're using R or Python. There are tons of really good, really well-vetted libraries out there. So sort of avoid the not invented here syndrome. When you're doing a lot of these projects, you'll find that they tend to sort of, your code tends to sort of split into 3 different levels, right? At the very bottom level, you'll have code that's specific to a single experiment within a given project, and so that needs to live in one place. A little higher up the hierarchy, you'll have stuff that applies to a given project, but might work for multiple experiments. So that might be things like labeling code. And then at the top level, you'll have utilities that your entire group uses across a range of projects. That top level utility code that's going to be used over and over and over again, you need to treat that as mission critical software engineering project, right? That means, JIRA issues, that means code reviews, that means change tracking, version control, the whole 5 yards. Metrics code deserves a special shout out. If you are computing accuracy or area under the curve or F1 score or anything like that for any of your sort of output statistics, everyone needs to use exactly the same code, right down to the same function, the same commit, every single time. Absolutely no exceptions. The reason for this is 2 different implementations of the same function can give you slightly different results. And when you want to compare the outputs of one experiment that Bob did to the outputs of another experiment that Alice did, and they're using two different functions to compute something like area under the ROC curve, you might actually end up getting that, hey, this looks better than this, when the reverse is true. So documentation, I love this quote, the only difference between screwing around and science is writing it down. Documentation, I like to think of it as enabling collaboration over time, not only within your team, but also with yourself. It's a continuous process. If you wait until the end of the project to do all of the documentation, you are going to hate your life. When you do your sort of group level utility code, that always needs to be well documented. When you have your final experiment that you're going to run and do the final analysis, document that code as well when you pass it over. Even if you're just doing like a modeling project where you're like, oh, I'm just going to hand them a black box and all they need to do is use it, plan on writing an after-action review so that in 6 months when you come back to a similar problem, you know what you did, why you did it, what worked and what didn't work. So keep some form of lab notebook as you go so that you can actually write that after-action report without going, oh God, what the hell did I do that one time? So I'm not going to go through all of these. I'm just going to say that these are questions that in a project, sorry, obligatory plug here, for the Aloha paper that the Sophos Data Science Group is going to be presenting at Usenix in a couple of weeks. We actually went through all of these and were very careful to sort of make sure we had answers to all of them, and the result was an exceptionally smooth sailing project. So common data set is probably the most important thing. If everyone is training models on the same data, on the same training data, and testing them on the same testing and validation data, you have no doubt that those results are directly commensurate and you can say, yes, this is definitely better than this. Other things like what are the right metrics, that should come out of your conversations with your external partners. Just simple things like, am I going to store stuff in JSON or CSV for like my experimental results? Documentation and like how to manage source code and how to structure your source tree. So from there, care and feeding of features, and you can think of this as also feature combinations if you're doing like a data science-y type report instead of an ML model. How often have you said one of these things to yourself? I can't get anything to work. I got it to work, but then I changed something in the code and it wasn't under version control, and now I can't remember what I changed and everything's hot, everything's garbage. Or it worked great on my machine, I don't know what the heck's wrong with the folks over in production. Couple weeks of this and you kind of end up about here. The way to avoid that is to heed well the 5 commandments of feature engineering. So step 1 is always, always, always talk to your domain experts, right? I think this was brought up yesterday as well. Talk to domain experts, heed well their advice. Feature extraction is critical. You got to track it. So when you run feature extraction code, you are not allowed to run it unless it's checked into version control. When you actually extract features, link those features to that commit. When you run an experiment using those features, link that experiment to those features that are linked to that commit. And then finally, when you're doing research feature extraction code, have test vectors. Right? Be able to say, I should put these 3 files in and I should get these 3 exact feature vectors out. Write that down, record it somewhere, save it for later. Domain experts are generally pretty accurately named. They're experts. They are a great place to start for getting features. Typically, a lot of, especially your really experienced analysts will have sort of this intuition of, that just didn't look right? Why did you flag this TCP stream? I don't know, there was something funky about it. Drill into that, right? Ask what the first thing they noticed was. Very often, they will have a well-established, carefully curated set of tools that they're extremely familiar with and can tell you exactly how to use. Very often these can be scripted. Very often these will be great sets of features. They'll also know they've been playing the cat and mouse game for years. They will know how the bad guys are trying to hide from them. Ask them about that, and very often those will actually be very good features themselves, right? PowerShell with a whole bunch of base 64 with null characters inserted in it. Right, got it. Stick it into a feature. Then once you've gone forth and you've constructed features and you've built some models and you're getting good results, take that feature extraction code back to them and say, hey, how would you mess with this? And prepare to cry bitter tears as they break it 10 ways from Sunday. So the security difference here, especially for stuff like PEs or scripts or things like VBA or what have you, tend to fall under antiforensics and the subsequent parsing headaches. So a lot of these things, right, bad guys very often use anti-reversing or obfuscation techniques, which are very common in their stuff, but within your total corpus of samples that you're going to be extracting features from might be comparatively rare. So, your feature extraction could be merely chugging along through all of your files, hits one of these obfuscated things or one of these things that's treated with anti-reversing techniques, and it'll suddenly crash or hang or eat up all of the memory on your box, or break in some other hilarious way. So make sure that when you're doing bulk feature extraction, you've accounted for these weird edge cases and you can recover gracefully so you don't, come back over the weekend and find that only 1% of your samples have been processed. Think about what you can do if feature extraction just cannot be done on some samples, right? Can you use models or do analyses that handle missing values gracefully? And then as new attacks, new evasions, new techniques come out, go back and constantly revisit your features in light of that. And finally, when you have samples which break your feature extraction, these are really great to set aside as test vectors, right? And so your test should be, I cannot process this feature, or I cannot process this artifact. Okay, so once we're through that, we're going to put the science into data science, and how we're going to do that is step 1, obey well Occam's razor. Start with simple baselines. Linear models are great, right? Simple, naive Bayes analysis is an awesome starting point. And sometimes what you'll find is you can just stop, right? I've run my random forest on it. It works beautifully. I talked with my external stakeholders a while ago, so I know what my metrics for success are, and I have hit them. Great, move on to the next thing. Sorry you didn't get to play with your awesome new, deep learning model. If you haven't hit that criteria, then at least having a good baseline lets you know what you are buying when you pay the price of adding extra complexity in terms of modeling or feature extraction or something. So always start with the classics. They are classics for a reason. Linear model, naive Bayes, random forest, decision trees. They tend to work really well and give you like a good starting baseline so you can get a good idea of how you improve in the future. So if we're being scientific, there's a couple of important questions that you want to ask yourself. Can anyone who's working on this project, right, you got a couple of people all working on the same thing, can anyone reproduce somebody else's results? right? Can anyone compare what they did with all of the results that have been logged, however it is you're logging? If you find a model that seems to do suddenly amazingly well, or find an analysis that seems to be incredibly predictive, can you explain what's different between that and all of the stuff that didn't work quite so well? And then when inevitably your project gets shelved and then 6 months later someone comes down and goes, oh no, we got to do it now, now. Can you pick up where you left off? Can you figure out what exactly you were, have you saved enough state to be able to pick it up off the shelf and keep going with it? The key to, so if you've answered yes to all of this, then you need to go back and ask yourself this again and make sure that you're really sure that this is true. So the key to all of this is some sort of experimental management framework. There's a bunch out there. Sacred and MLflow are two that we've experimented with, and we've been happy with both of them. But really what you want is you want to be able to push one button, say, run this experiment, Python experiment.py, and then save everything, and save it in a consistent format, and you've already agreed with the rest of your team what you're going to record and how you're going to record it. You get dependency information, you get critical source code, you get which features went with which feature extraction function. And finally, make it force you to write down notes. I'm doing this run to look at this question. And if you have all of that saved in one place, then coming back to it in 6 months should be pretty straightforward. So, know when to shift gears. So, again, when I'm doing these things, I tend to sort of think of them in 3 stages of escalating complexity. The first one is tinkering. I've got some problem, I've got some data, I'm going to fiddle around with it, I'm going to try some stuff, and I'm going to see just what seems to work, right? Do I have some good plots, some good visualizations, some quick off-the-shelf stuff I can try? So this is like done at a read, evaluate, print loop, or in a Jupyter notebook or something like that. Once I've got some good candidates for what seems to be doing okay, that's when you move to testing. So you're going to scale it up. If I scale it up, does it keep working? Are there particular variants on this problem that seem like they're worth full-scale test? So at this point, you should be splitting it out into scripts. You should have some basic logging in place. You should maybe be saving some artifacts manually. And then you get into sort of the rigorous study phase. And at this point, you're doing testing almost at full scale. This is where your hyperparameter searches come in. This is where you're doing sort of more detailed analysis and really like pulling apart what you've found in your sort of exploration of the data. And at this point, what you really want is clean code, version controlled, in a framework. So I am prepared to die on this hill. Jupyter notebooks are great for starting out. They're great for small-scale one-off projects. They're great for reporting, for writing reports. For actually doing large-scale collaborative data science research, I think they are kind of a disaster. They make things really difficult. So go ahead and argue with me. We'll have beers or coffee or tea and fight it out. So, do your experiments support your conclusions? This is always a good question to ask, right? If I change 3 things at once, I don't know which of those 3 things actually gave me an improvement. Very often there is a random element in a lot of analyses. So if you're doing k-means clustering, right, where those means start can sometimes affect what your final clustering is. If you're fitting a deep learning model, how the weights are initialized can affect your final performance. So when you've got something that seems to be really good, run it a couple of times, repeat that experiment, get some idea of the variance in these statistics that you're reporting. Finally, you need to be really critical of your own work before nature has a chance to do it to you. So think about how you could have possibly screwed something up. So, do your data support your conclusions? So not all metrics are meaningful. If you've been talking with external stakeholders, you should be beyond that. Not all measurements are precise, especially when you're dealing with label noise. And very often, you won't have enough data to measure what you want to measure. And I'm sorry for the quality of this, but I thought this photo was like too perfect not to bring up. So this is a actual baseball game that I went to, and you can see at 5:31 in the afternoon, the right fielder had a batting average of 0. Just before he went up to bat. At 5:35, after the right fielder has had his at-bat, he now has a batting average of 1.0. What's the right number, right? So that was, if you go back and you look at his stats, it was obviously his first at-bat. He got a hit, so, 100% of his at-bats, he's gotten a run. or he's gotten hit. So, sometimes you need a lot of data to get a really good estimate of something. And if you don't have it, you shouldn't be reporting those statistics. So again, the security difference here is noise and drift. You always, in security, are going to have, almost always, are going to have errors in your labels. So this can very easily lead you to over or underestimating error rates, especially if you've got systematic errors in your ground truth labels, right? My machine learning models are really awesome at picking out these DOS viruses that I've had, years and years and years to analyze and pull apart and disassemble. That may make me overly optimistic about the performance of my model because I'm never going to see those in the wild, or almost never. If I've got a 1% error rate in my labels and I'm reporting a 0.01% difference between two models, is that really meaningful? You gotta, it's make sure that your statistics are not being distorted by the noise that's in your labels. And again, adversarial drift or even just plain old drift is always a concern. So think about, can you measure how fast your data distribution changes over time? Think about if old data could be biasing your performance estimates. And then especially in the security space, as you start implementing solutions or implementing detection models or taking action based on your security analyses, you're going to change the data distribution, right? If you find, here's all of these misconfigurations, we can now detect these misconfigurations, we'll go tell them to fix these misconfigurations. Those misconfigurations are no longer going to appear in your data. So you've sort of moved that distribution of data. Okay, so how to deploy without just throwing it over the fence. These next two sections are going to be kind of short because they are sort of inherently company specific, but I'm going to try and talk about, having been in a couple of places, ways that, or some common themes that have come up. So, you have been talking with your customer the whole time you've been working on this project, right? As long as you have, you should be actually in pretty good shape, right? They should know what the model, what the analysis covers, what the assumptions going into it are, what sort of data is going into it, what sort of results and conclusions are coming out. And if you couldn't analyze some stuff, or you just couldn't get access to some data, or you think that there's a data bias, you should have told them about that, right? They should know sort of what the potential red flag areas are for this and where they might want to be a bit cautious about applying the results or the conclusions. So if needed, in your documentation, in whatever you pass over to them, in your nicely written reports and summaries and meeting minutes, you should be able to explain what you did, why you did what you did as far as modeling or analysis. This is also a great place to mention samples that don't parse well and you can't analyze, feature issues where you might have missing data or you might want them to try and collect more data and stuff like that. Okay, so if you've got all that under control, then basically here's what's left. A good starting point is always, if you're delivering a model, give them a mock-up, a Docker container, a SageMaker instance, whatever it is, however you're deploying it. Give them something that just takes the right inputs and gives out the right outputs so they can do integration and smoke testing. Do whatever you've decided you're going to do to convert your model from research to production, be that putting it all in a DLL or putting it in a Docker container or just handing them over a bunch of scripts, right? As long as you've agreed on it, that's all good. Once you've done that, remember I talked about test vectors? This is where they're going to save you an unimaginable amount of time, pain, and money. Run your samples through your production feature extraction and through your research feature extraction and make sure that they match up. Run your production model on your research features, run your production model on your production features. Make sure those match up. Make sure that your production feature extraction fails on the same stuff that your research feature extraction does, right? Make sure all of your test cases pass, basically. This is sort of a rule written in blood by us. Once you've finished all of that, package and do the handoff, right? You've got some sort of conversion procedure, do it, toss it off, and you're done. So super easy, right? No. So in practice, every time you do this, it's hard. It's especially hard the first time. So again, I know I keep harping on this, but you got to talk to the people that you're handing these reports or these models off to. Be flexible about how you deploy, but not too flexible. You want to get this standardized and repeatable as fast as you can. Every time you go, okay, we're just going to do it as a one-off this one time, and just to get this out the door, you are accruing technical debt that will be harder and harder and harder to pay down. The faster you can get this standardized, the better off you're going to be. So again, the security difference here, this tends to be sort of a culture gap thing. The high level takeaway point is you're dealing with probability and aggregate statistics, not individual artifacts. So if your model gives the wrong conclusion on a single sample, it happens. If it gives the right conclusion on a brand new sample, it happens, right? Don't despair or celebrate either way. Machine learning models in particular always are going to have false negatives and false positives. You need to have some process in place to detect those and to work with those, or to plan around them, or to mitigate the errors that, or the problems that those errors might throw up. People, especially people rooted in a more sort of traditional security background, sort of thinking of like reverse engineering malware or writing signatures, very often will try and drag it back down to a population or to a sample level discussion, right? Your model missed this sample, your model didn't catch this flow, and sort of, again, trying to educate and communicate to them that really what you're looking at is like population level, right? Yes, it missed that one, but it catches 98% of the other stuff. That's the message that you want to keep trying to communicate to them. Did it work? This is where telemetry comes in. So you are getting telemetry, right? If you deploy the model and you never hear anything else, in 6 months, you will have no idea if your analysis is still valid, if your model still works, if your process is still, monitoring the correct statistics. Try it on real data. If you can't get the real data to come to you, send the model to them and run it in some sort of silent mode for a while, right? And get feedback from that. Check and make sure that the real data actually looks what you expected, right? So sometimes you might get a description of the data from your end customers, and then you go and you actually look at it and you have no idea what you've just been shown. So make sure that those kind of match up. If you're getting telemetry, you're getting results, you're running the data through your model or through your analysis, you should be able to tell whether or not it's adding value. Are you catching new stuff? Are you mitigating errors? If you've got some sort of metric that you've deployed, is it tracking what you thought it was tracking? Can you use the model to collect real-world data for later refinement and training, right? It's going through some process that you have some limited degree of control over already. Can you negotiate with them to say, well, yes, this Docker container or whatever it is, it'll give you the results you need, but it's also going to send some data back to us, right? So that's one avenue that you can collect real-world data. But again, go back to the earlier slide where I was talking about the risks of holding on to data, right? Make sure that you discuss it with everyone who's involved, and then discuss it again, and then go talk to legal. The security difference here is model decay. It works great until it doesn't, basically. Over time, things change, metrics degrade, models fall apart, adversaries adapt and evolve. So you always want to be cross-checking your performance against new threats, new attacks, new campaigns. And again, this is talking to the domain experts, right? When they see a new family of malware pop up, grab some samples from them, run them through your model, and see what comes out. All of these things eventually have to be retrained, reanalyzed, redeployed. You need telemetry to tell you when it's time to do that. Okay, so to wrap up, what exactly did we learn from all of this? Hopefully this. At the end of the day, what you want to do is you want to deliver a data science project that somebody wants. The analysis should be useful to them. The metric should have a business impact. The model should detect something interesting, and so on. The way you find out what somebody wants is by talking to them. So talk to your stakeholders. You should do good science. That means a lot of things, but mostly it means being systematic, being reproducible. And then make sure that you've delivered what it is they wanted. They know what they're getting and how to use it, and make sure that you can track what you've delivered and be able to tell when it's not working anymore. And above all, you want to build this into your daily routine, right? Build processes that let you do this so you don't have to think about it anymore. With that, I know I'm a little bit early, but that gives you time to ask me questions, and I am contractually obligated to make you stare at this slide for just a second.
Hi. I'm guessing that your team mostly works in the domain of file analysis. Is that accurate?
Yes.
Follow-up question. I guess the new EDR product from Sophos, you have the same sort of process and network telemetry as most of the other products. Is your team doing anything with that sort of time series data set?
So we are working on, there are projects in the pipeline for machine learning on network traffic, and I think that's probably as much as I'm allowed to say.
So you spoke a lot about the importance of collaboration, and in particular collaboration within the team that's working on the particular project. And I'm curious if you have advice for people who maybe have a much younger security data science practice, and maybe they're the only one working on that problem at a given time. How do you suggest that they go about externally validating, so to speak, and getting that feedback from their peers when they don't really have a ton of peers?
So, like, not a ton of peers within the organization?
Yeah, not within the organization.
So I think at that point, presenting at conferences like this is great, right? So this is a good place to sort of to vet your ideas. You know, reaching out to other people that are working in the same space and talking with them is always a good idea. Very often you can sort of sanity check yourself against the academic literature and just sort of see what are other people working on, and do they seem to be having similar intuitions as I do. A lot of it, even within sort of a one-person data science practice, though, you can still be sort of systematic and rigorous and reproducible. And sort of building those good habits in gives you a jump start on doing things like presenting or publishing papers and, you know, getting feedback from that. Another thing that can be, I know it's intimidating for some people, but I think it's super useful, is actually writing academic papers, right? Submitting to conferences and getting feedback on your work from that. Even if the paper gets rejected, very often you'll get very useful feedback on ways the analysis could have been improved or ways the presentation could have been improved.
Thank you.
So you talked about reproducibility, which is one of my huge touch points. But you also mentioned storing your data in like CSV or JSON. Have you looked at any using database with provenance at all, or to systematically, you know, keep track of stuff?
So a lot of times the results that we store tend to be like very, very large. So like we could be, just as one example, in the paper that I alluded to that went to Usenix, our test set was 7 over multiple experiments. So we didn't look at a database with provenance, but we did look at storing sort of all of the results in SQL to be like queryable and cross-checkable. And it turned out to not really be feasible for us between multiple people running experiments at the same time and writing stuff to like different files. So for us, storing stuff in CSV and then compressing it ended up being the best result. But yeah, I mean, looking at something with provenance, actually, it seems like a really good idea now that you mention it.
Thank you.
Hi. You talked about using Jupyter as a great reporting tool, as for singular analysis as a scientist. Mm-hmm. For collaborative research or reporting, it doesn't scale. So what do you guys use instead?
So this is totally personal opinion at this point, and I will fight it out with anyone. What works best for me is having key functions in scripts that are version controlled, that are going through a change management process of some sort, importing those into the Jupyter notebook to write up here's my report on the conclusion of this experiment. You import all of the stuff, you import the data, don't actually run the model fitting and training within your notebook. Do the training elsewhere. It's great for presenting and slicing and dicing and analyzing data. I do not find them particularly useful, especially when you're writing functions within the Jupyter notebook, because then you're copying the same function from notebook to notebook to notebook. You're tweaking it in every different notebook, and suddenly you have to remember which version of which notebook had this magical feature extraction function that actually worked. So if you're importing stuff from well-structured Python libraries into your Jupyter notebook and then running a data analysis, it's awesome. Use it. When you're actually doing like hyperparameter search or something, my own personal opinion is that should be done sort of in scripts through an experimental management framework. I also found that Jupyter notebooks don't tend to play terribly well with version control. You rerun it and all of a sudden everything changes and you've got a new version, even if all you did was rerun the same cells through it. So that's a pet peeve of mine, which is another reason I don't typically like them.
So my question is more along if you're sharing with other people looking at the same time, think of like Google Sheets or Confluence or some sort of wiki page that someone can watch you as you're doing it. Do you use some sort of tool that's collaborative as you build the reports or work? Let's say if someone's what sort of pair programming, something similar to that, you're teaching someone, are they just watching over your shoulder literally, or is there some sort of tool that you use that's similar to Jupyter?
Yeah, we don't tend to do that sort of, watch me program this analysis in real time type stuff. We tend to sort of do it internally and then deliver static reports. Jupyter might work great in that use case. I don't think we've ever tried it though.
Okay, thank you.
How's it going? Is there a threshold of data that you use for your modeling that you consider the most optimal? Is it like 1 year or 3 years worth of data, whereby 5 years would be too much because it gets too skewed because things change over time? And the second part of my question is regarding, do you collect it all, or do you remove out things like seasonality trends or cyclical trends that maybe exist inside the data that you're collecting?
So I'm going to give you the really weaselly answer to that question, and I'm going to say it depends on the problem. So for stuff like malware, you very often, actually for a lot of security problems, what you're less interested in, there are some seasonal things you can see, like everyone getting busy as everyone goes on like Christmas vacation or something like that. But in general, what you're more interested in is sort of weird one-off bursts that occur as the result of a new campaign, or someone finds like a new exploit and drops a POC for it and it goes everywhere. As far as how much data is too much data, again, it's really, really problem dependent. So when we're looking at things like URL data, just detecting malicious URLs, that seems to age out very quickly. So we've done sort of our internal analyses of that, and I think we've come to the conclusion that we really only want to save a couple of months of that kind of data. Whereas for malware, it seems to have a much longer shelf life because you definitely do have some like oldies but goodies that just keep coming back over and over. And so you want to keep those in your training set. So yeah, it depends. I think it's an analysis that needs to be done on a problem-by-problem basis, but it should be part of your analysis.
Hi again. How much time is spent on the hyperparameter searching and testing phase, and is that automated?
It depends, and yes. So again, very often a lot of it comes down to what is our threshold for success. So if something really simple works right off the bat, or we have a couple of sort of, in addition to like logistic regression and random forest and gradient boosted decision trees, we have a couple of stock architectures that have seemed to work really well on a large range of problems. And we tend to just throw them at them and see what pops out. And a lot of times, because we've sort of set our thresholds for success and our criteria for our exit criteria, we run one of those, it works great, and we're like, good, ship it, done. If it needs hyperparameter search, then yeah, there are several Python packages out there that will do hyperparameter optimization for you very effectively, and you just throw it at one of those. But again, all of this happens inside an experiment management framework, so that when you run that hyperparameter optimization, you know what the range of hyperparameters you tried was, and you know what it did, and what the results are, and they're all automatically stored and tracked.
Hi. You mentioned earlier about regulations around data retention and stuff like that. How do you make solid cases for retaining for longer periods of time than what you would normally have to be held to by the decisions of like your legal departments and stuff like that? Because sometimes some analyses really only have value if you have data outside of that scope.
Yeah, and that's something that we have to negotiate with legal, right? We have to get their approval to be able to hold on to that kind of data. And again, what it comes down to is sort of doing the work behind it to show, no, if we restrict ourselves to 3 months of this particular data type, the results are going to be too bad for general use. And so we really need 6 months or a year or 2 years of this in memory. And this is being able to show your work on that and show that you actually have considered only holding it for 6 months, and you're not just doing the standard data science thing of, no, we couldn't possibly throw away any data ever, tends to give you at least a little bit more of a firm ground to stand on when you're trying to negotiate these things. But at the end of the day, if the legal department comes through and says, no, you just cannot keep it, right, that's the end of the story, right? We just tell them this is the business cost of not keeping this data, and someone decides that they're going to pay it.
All right, let's give another round of applause for Rachel.